So the notes start by talking about how a linear map can have different matrix representations. It all depends on the bases you choose.
Right. We've used a standard basis before where everything's nice and easy, but what happens if we use a different set of vectors?
The notes say that if we fix different bases, we'll get a different matrix representation for the same linear map.
That makes sense. The matrix is just a set of instructions, so if you change the coordinates, the instructions have to change too. But the big question here is, how do we relate these different matrices to each other?
Exactly, and that's what this whole section is about. Before we get to the new stuff, the notes review the definition. Let's say we have a basis for V called BV and a basis for W called BW. The matrix representation of the linear map F is a matrix A such that F of V1, F of V2, dot, 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 F of Vn equals W1, W2, dot, 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 Wm, A.
Okay, so the output vectors, f of vj, are a linear combination of the basis vectors of w with the coefficients coming from the columns of matrix A. What does that actually mean, though?
The next page shows us what that means in an equation. F of Vj equals the sum from I equals 1 to m of Aij Wi.
Oh, so the jth column of A gives us the coefficients to write the output vector, f of vj, in terms of the basis vectors of w. That's a much clearer way of thinking about it.
Okay, let's keep going. We're skipping to Theorem 1, which talks about composition. If we have a linear map F from V to W and a linear map G from W to U, and their matrix representations are A and B, defined by F of V1, F of V2, dot, 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 F of Vn equals W1, W2, dot, 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 Wm, A, and G of W1, G of W2, dot, 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 G of Wm equals U1, U2, dot, 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 ULB, then the matrix representation of the composed linear map G circle F is BA.
Wait, G comes second, but its matrix B comes first in the product. Is that right? Why isn't it AB? That seems backwards.
The notes actually prove it. Let's try to follow along. They assume the matrix representation of G circle F is a matrix C. G circle F of V1, G circle F of V2, dot, 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 G circle F of Vn equals U1, U2, dot, 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 ULC. Then they substitute in the definition of F of Vj and use the linearity of G. G of F of Vj equals the sum from I equals 1 to m of Aij Wi, which equals the sum from I equals 1 to m of Aij G of Wi. Now we substitute in what we know for G of Wi from the definition of B. G of Wi equals the sum from k equals 1 to L of Bki Uk. And finally, we get G of F of Vj equals the sum from I equals 1 to m of Aij times the sum from k equals 1 to L of Bki Aij, all times Uk.
Oh, I see it now. The term in the parentheses, the sum from I equals 1 to m of Bki Aij, is exactly the definition of matrix multiplication. That's the element in the kth row and jth column of the product BA. So the matrix C is indeed BA. That makes me feel a lot better about the order.
The next page has Theorem 2, which links a linear map's properties to its matrix. Theorem 2 says that if a linear map F from V to W has the same dimension for V and W, then F is an isomorphism if and only if its matrix representation, A, is invertible. And the inverse map A inverse is the matrix representation of the inverse map F inverse.
So a linear map is invertible if and only if its matrix is. That's a super neat connection, and the matrix for the inverse map is just the inverse of the original map. I like that.
The notes move on to the core topic, change of bases. They define a linear transformation phi from V to V that takes one basis, BV, to a new basis, B prime V. The notes state that phi is an isomorphism.
Why is that? What makes it an isomorphism?
Well, we have a basis B prime V, which is a set of linearly independent vectors that span V. Our map phi takes the basis BV and maps it to B prime V. Since the image of a basis is a basis of the same vector space V, the map has to be an isomorphism. The notes then define a transformation matrix P. Let P be the matrix representation of phi, V'1, V'2, V'N equals V1, V2, Vn, P. Then P must be invertible because of Theorem 2. This P is called a transformation matrix.
The notes say to be careful. It says P quote-unquote translates B'V into BV, but the equation shows the new basis on the left and the old basis on the right. Shouldn't P transform the old basis into the new one? That's confusing.
Yeah, the wording is a little tricky. Let's think about it this way. The columns of P are the coordinate vectors of the new basis vectors V'I with respect to the old basis Vi. So P helps us write the new basis in terms of the old one. So P is the change of basis matrix from the old basis to the new one. So the notes are kind of right. P takes the vectors of B'V and expresses them in terms of BV. It's just a little awkwardly worded. Now we get to the main event. The notes lay out the scenario. A linear map F from V to W. We have two bases for V, BV and B'V, and two bases for W, BW and B'W. The notes say that F has two matrix representations, A and A'. F of V1, F of V2, F of Vn equals W1, W2, Wm, A, and F of V'1, F of V'2, F of V'N equals W'1, W'2, W'm, A'.
The big question is, what is the relationship between A and A'?
Let's follow the notes. First, we consider the basis transformation for V. V'1, V'2, V'N equals V1, V2, Vn, P. We apply F to both sides. F of V'1, F of V'2, F of V'N equals F of V1, F of V2, F of Vn, P. And we know that F of V1, F of V2, F of Vn is equal to W1, W2, Wm, A. So we can substitute that in. F of V'1, F of V'2, F of V'N equals W1, W2, Wm, AP. The notes call this equation star. Now we need to consider the basis transformation for W. W'1, W'2, W'm equals W1, W2, Wm, Q. Since Q is a transformation matrix, we know it's invertible. W1, W2, Wm equals W'1, W'2, W'm, Q inverse. Now we substitute this into our equation star. F of V'1, F of V'2, F of V'N equals W'1, W'2, W'm, Q inverse AP. And we know from page 12 that F of V'1, F of V'2, F of V'N equals W'1, W'2, W'm, A'. So we have our answer. A' equals Q inverse AP.
Wow, that was a lot, but I think I get it. To get the new matrix, A', we take the old matrix A and we sandwich it between the inverse of the W basis transformation matrix and the V basis transformation matrix. It's like a recipe for changing a matrix.
That's a good way to put it. The notes also give us a visual to help. A' is a composition of 1, P, which translates B'V into VB, 2, A, which maps BV to BW, 3, Q inverse, which translates BW into B'W.
Why do we have to use the inverse of Q? That's the one part that's still a little fuzzy.
Let's look at the diagram. We start with a vector in the new basis for V, B'V. P takes that vector and gives us its coordinates in the old basis, BV. Then we use the old matrix A to map it to the old basis for W, BW. Now we want to express that result in the new basis for W, B prime W. We know that Q takes vectors in B prime W and gives us their coordinates in BW. So to go the other way from BW to B prime W, we have to use the inverse, Q inverse.
That makes perfect sense. The P matrix gets us to the old bases, A does the actual work, and the Q inverse matrix gets us to the new bases.
The last page we need to look at is Corollary 3. Let A and A prime be the matrix representation of a linear transformation F from V to V with respect to bases BV and B prime V respectively. Then A prime equals P inverse AP, where P is the transformation matrix from BV to B prime V.
Okay, so this is just a special case of the previous theorem where V and W are the same space, so Q is the same as P. That's much simpler.
Exactly. This is an important one because it's so common to change bases for a linear operator that maps a space to itself.
Well, I think that's all we can get out of these notes for now. My brain is a little full.
Same here. But I think we have a solid handle on how a change of basis affects a matrix representation. The main thing to remember is that you're just transforming the coordinates, not changing the linear map itself.
Yeah, and that the order of the matrices matters. Thanks for walking me through that. I feel a lot better about it now.
No problem. This stuff is a lot easier when you talk it out.
You know, I was dreading this chapter, but it's not so bad when you have someone to help.
Glad I could help. Want to grab a coffee before we start the next topic?
You read my mind. Let's do it.